This video tells the story of the formation of the Earth, which we believed happened 4,500 million years ago. It tells of a solid and liquid iron core, a solid but fluid hot rock mantle, and a solid rock crust with the liquid oceans and gaseous atmosphere on the surface. The early universe was made up mainly of hydrogen and some helium. These formed stars as they were pulled together by gravity. In these stars, the elements up to iron built up. When very large stars exploded, the so-called supernovae, the remaining elements of the periodic table were formed and scattered into space. It was from this debris that our Sun and solar system were formed. So we are all made of stardust. Planets closest to the Sun lost their hydrogen and helium atmospheres, still seen in the gas giants like Jupiter. This left the early Earth made of liquid rocks and metal, heated by the gravitational impact of the debris from which the Earth was formed. Our Moon was probably formed from a collision between two early planets, since the Moon shares much the same age and rock composition as the Earth. When the Earth was still very hot, the dense iron sank to form a solid inner and molten outer iron core. It is this liquid iron that is responsible for the Earth's changing magnetic field. The lighter rocky material, made mainly of aluminium and magnesium silicate, formed the hot solid mantle. Although the mantle is solid, it is able to flow rather in the same way that solid ice flows when glaciers flow down mountains. Finally, there's the solid crust, which is a relatively thin layer of basalt, mainly magnesium silicate and a silica mix, made from fully solidified magma, with the lighter continents, mainly made of less dense granite, which is aluminium silicate and silica mix, effectively floating on this crust. As you can see in our video on plate tectonics, our continents have been ferried around the globe, split up and merged again and again over time, but essentially these continental rocks have remained floating around since the early days of the Earth. Outside this solid Earth are the oceans and the atmosphere. The early atmosphere, held tightly to the Earth by gravitational attraction, would have been composed mainly of nitrogen with some carbon dioxide and water vapor. There was no oxygen in the atmosphere, as it had not yet been introduced through photosynthesis. We have a video that tells that story. As the Earth cooled, the water vapor condensed to form oceans. Over time, the soluble salts in the rocks dissolved in the rain, which flowed to the oceans, making them salty as we know them today. We have pieced together this story through many different methods. Earthquakes produce two sorts of vibrational waves: P, primary pressure waves like sound, and S, secondary transverse waves like waves on the sea, except that these waves cannot pass through liquids. Their speed is determined by the different densities of the core and mantle, and this enables us to use them as they travel from one side of the Earth to the other to work out the composition and the layers. The age of rocks is determined mainly through radioactive dating. When a radioactive element, such as potassium-40, undergoes radioactive decay, a decay product is formed, in this case argon-40, which builds up in the rock once the rock solidifies. Using the half-life of the element, in this case 100 million years, we can estimate the age when the rock solidified by how much decay product there is compared with the amount of starting element. For example, if there's an equal amount of potassium and argon, then the rock would have solidified 100 million years ago, long before the dinosaurs became extinct. To summarize, the study of earthquakes and radioactivity has taught us about the composition of the Earth. It consists of a solid and liquid iron core, a solid but fluid hot rock mantle, and a solid rock crust with liquid oceans and gaseous atmosphere on its surface.